Hello everyone, I am Sushil Varma, a third year PhD student in School of Industrial and Systems Engineering, Georgia Tech, advised by Professor Siva Theja Maguluri. Today, I will be presenting my recent work on with my advisor titled A Heavy Traffic Theory of Two-Sided Queues. The presentation is divided into four parts. I will first motivate the analysis of a two-sided queue, then I will formally present the model and the results, followed by a high-level proof idea. Lastly, the talk will be concluded with a brief discussion on how these results and proof techniques can be applied to a single server queue with state dependent arrival rates as well. Let's start with the introduction. Our work is motivated by analyzing marketplaces. A traditional marketplace is generally composed of a single supply entity and multiple buyers. This can be modeled by a single server queue or a network of single server queues. Some of the applications include cloud computing, manufacturing, communication networks, etc. There is a long line of literature studying these systems, and one of the first works date back 1,000 years. On the other hand, gig marketplaces have multiple demand as well as supply entities. A fundamental queuing model in this case is a two-sided queue with both customers and servers arriving into the system. Some of the examples of such a marketplace include ride hailing, meal delivery, grocery delivery, etc. These are emerging applications and the literature of two-sided queue is relatively new. Now let's take a quick sneak peek into the literature of two-sided queues. There are many models introduced in the literature that are closely related to a two-sided queue. Without going into much detail, I would like to point out that most of the literature focuses on transient analysis and there are only a few papers that conduct steady state analysis. On top of it, our work conducts a more fine-tuned analysis compared to the literature on steady state. In particular, we believe we are the first ones to completely characterize the distribution of the delay in two-sided queue in heavy traffic limit. Now let's talk more about the model and the results presented in the paper. We refer to demand as customers and supply as servers. In a two-sided queue, there is a waiting area for customer and servers. Both of them arrive into the system and wait until they are matched. As there is no incentive for both customer and servers to wait at the same time, they are matched as soon as there is a compatible pair in the queue. Thus, only one of the queue is non-empty at the same time. Note that for any value of lambda and mu, the queue is unstable as either one of the queues will blow up when lambda is not equal to mu, and when lambda is equal to mu, the underlying Markov chain will be null recurrent. Note that our definition of stability is positive recurrence. Thus, we need an external control to make the system stable, which can be done using dynamic pricing. In particular, the arrival rates can be a function of queue length. Now we can analyze the system in steady state. Let's consider the model in more detail. We consider a two-sided queue operating in discrete time with state-dependent arrival rates. The state of the system is the imbalance, that is the number of customers minus the number of servers waiting in the system. The arrivals are governed by any general distribution with a finite support, and the queue evolution equation can be given in terms of customer and server arrival rates. In particular, the imbalance in the next time epoch is equal to the imbalance in the current time epoch plus the number of customer arrivals minus the number of server arrivals. Similar to a GG1 queue, it is challenging to analyze a two-sided queue with general arrival distributions. Motivated by the comprehensive literature on GG1Q, we aim to analyze a two-sided queue in heavy traffic. However, the definition of heavy traffic is not trivial, as we need the expected arrival rate to be equal to the expected service rate in steady state for stability. Thus, we consider alternate interpretations of heavy traffic in a single server queue. One of the first interpretation is the external control vanishing if we interpret epsilon as an external control. We can also interpret heavy traffic as a phase transition from positive recurrence to null recurrence. Based on these two interpretations, we define heavy traffic in a two-sided queue as the limit the external control goes to zero, that is phi c and phi s converges to 0 uniformly. We do this by parameterizing the arrival rate by epsilon and tau, where epsilon scales the magnitude of the control and tau determines how far away from the control from 0 the control is applied. Heavy traffic is then defined as the limit epsilon goes to 0 and tau goes to infinity. Note that now phi c and phi s are given functions which do not change, and only the two parameters epsilon and tau changes and converges to their respective asymptotes. Based on how fast these parameters goes to their asymptotes, a phase transition is observed. We present the phase transition by first considering the following illustrative example. The arrival rates are simple threshold policies. That is, the arrival of customer decreases by epsilon if there are more than tau customers in the system, and similarly for the server. In addition, the arrivals are governed by a simple Bernoulli arrival process. The underlying Markov chain is then a simple birth and death process, and we can calculate the stationary distribution of the imbalance in closed form. However, to illustrate the phase transition, we characterize the distribution of the scaled imbalance in heavy traffic. When epsilon tau goes to 0, we observe that epsilon z, the scaled imbalance, converges to a Laplace distribution, a two-sided exponential distribution. This can be interpreted by considering the case when tau is a constant and epsilon converges to 0. Such a heavy traffic limit is similar to the classical heavy traffic limit in a single server queue, and thus we observe the two-sided equivalent of exponential distribution. Next, when epsilon tau converges to infinity, we observe that z by tau converges to a uniform distribution. This can be interpreted by considering the case when epsilon is constant and tau converges to infinity. Outside the threshold tau, there is a non-zero drift that pulls the system back into the threshold, which results in a uniform distribution between the thresholds. Lastly, when epsilon tau converges to a constant, we observe a hybrid of the Laplace and uniform distribution, which clearly illustrates a phase transition from Laplace to a uniform distribution. To gain further insights, we plot the distribution of epsilon z on the left and z by tau on the right for different limiting values of epsilon tau, denoted by L. We clearly see that as L converges to 0, the distribution of epsilon z converges to a Laplace distribution, and as L becomes larger, the distribution of z by tau converges to a uniform distribution. The main result of the paper generalizes this said phase transition phenomena to a general class of arrival rates and a general distribution of the arrivals. In particular, we consider arrival rates given by general functions phi s and phi c, and parameterized by epsilon and tau. The arrivals are governed by a general distribution with finite support, and we impose a few weak assumptions on the arrival rate functions to ensure stability and make them amenable to analysis. We first present the result in the case when epsilon tau converges to a constant. We show that the scale imbalance converges to a Gibbs distribution, also known as Boltzmann distribution. The function that defines the Gibbs distribution depends explicitly on the mean and variance of the arrivals, similar to the limiting result on a GG1Q. To further understand this result, consider the limit as L converges to 0. Note that the function g1 converges to a function that only depends on the sign of the imbalance. Thus, you can intuitively see that the Gibbs distribution converges to Laplace as L converges to 0. We show that this intuition indeed holds true, and epsilon z converges to a Laplace distribution in the case when epsilon tau converges to 0. Similarly, consider the case as L converges to infinity. Note that the PDF of Gibbs distribution vanishes everywhere except when the integral of G2 attains its minimum. Thus, Gibbs distribution converges to a uniform distribution with the support equal to the set where the minimum is achieved. This motivates us to state the following result without a proof due to technical challenges. In particular, in the case when epsilon tau converges to infinity, z by tau converges to a uniform distribution with support equal to the set where the minimum is achieved for the integral of the function g2. Now we briefly present the proof idea used to prove the result in the case when epsilon tau converges to a constant. We devise the novel inverse Fourier transform method, which comprises of mainly three steps. First, we show tightness and positive recurrence of our system. This ensures the existence of a random variable z infinity such that epsilon z converges to z infinity in distribution. Next, we set the drift of the characteristic function of the imbalance to 0. After taking the heavy traffic limit, we obtain an implicit equation in terms of the characteristic function. To solve this implicit equation, we we take the inverse Fourier transform. In particular, we observe that the characteristic function of a random variable is same as the Fourier transform of the PDF of that random variable. Denote the PDF by f and note that we can write this implicit equation in terms of Fourier transform as follows. Next, we'll take inverse Fourier transform on both the sides to obtain a differential equation in terms of the PDF of the random variable z infinity. We can now just solve this differential equation to obtain the distribution of the scaled imbalance. Note that this is just a back of the envelope calculation and does not comprise a formal proof. However, this idea can be formalized using the theory of Short's function and tempered distribution. We will conclude our presentation by discussing a single server queue under general distribution and general arrival rates. Similar to a two-sided queue, consider a single server queue with arrival given by the function phi c and parameterized by tau and epsilon, and the server arrival service rate given by phi s and parameterized by again tau and epsilon. We again observe a phase transition from exponential to uniform via hybrid distribution in the case of Bernoulli arrival and threshold based policies, and um, again a phase transition from exponential to uniform via one-sided Gibbs distribution for general arrivals and general arrival rates. Similar to a two-sided queue, we leave the case of uniform as a conjecture here as well. This concludes our presentation. If you have any further questions, I would be happy to answer them now. And I'm really looking forward if you have any comments about this piece of work. Lastly, I would like to thank the conference committee for all their hard work on putting up this conference in such challenging times. Thank you.